You're on.
All right. Hello, everyone. Friends, family, faculty, and those who are just here for MECI 312 sympathy points. Thank you guys very much for coming to our senior design presentation. We are very excited to get to tell you about what we've been doing throughout this whole year. We are the Firefighting Robot Capstone Design Project for 2019. My name is Bryce Kulik, and I'm going to get to tell you a little bit about the overview of our project so far. So before we go into the actual details of how we did it, I would love to share a bit of a brief detail of what we are doing. Essentially, our task this year was to build a fully autonomous, self-driving car that can also put out fires. So it's a firefighting robot, more or less. This firefighting robot was to be entered into the same standards that the Trinity College Home Robot Contest has set up each year. And so that includes a lot of size constraints, weight constraints, as you can see up top. And essentially, they would just put it into a box and make sure that it could fit within those size and weight constraints. And it had 3 levels of a competition. Each one of these levels had different tasks and different objectives, and our robot was attempting to complete as many of these objectives as we possibly could. Level 1 was pretty simple. You just had a maze, and you had to navigate throughout the maze and find a candle and extinguish it. This is something similar to what many of you might have experienced over in Hoyt if you got to come and visit and see it actually run its demo. Level 2 included a lot more imperfections. It had furniture and dogs and mirrors and stuff to throw the robot off. And then level 3 included a lot harder tasks, including picking up a baby with some arms and locating it back to a safer spot.
My name is Nathan Hare. My main task on this project group was electrical designer, and I also took care of some of the finances as well. So as Bryce described, once we knew our task and what we had to do, we decided to pick out some motors. So we chose this drive motor kit. This would give us the correct speed we would need to complete the task in the time that we were looking for, as well as it also had encoders that came with it, which would save us some time. After that, we needed to figure out how we were going to power it. So for that, we chose 2 of these 11-volt batteries that we ran in series. From there, we converted them with DC buck converters for 12 volts and then 5 volts. The 12 volts ran the motors as well as some of our servos, and then actually the 5 volts ran the servos, but the solenoid was run off the 12 volts. Then the 5 volts also run most of our electrical components. So then next we chose some of our electrical controls. The most important one probably being the O-Droid right here. This was in charge of a lot of the LiDAR processing, which Wyatt will be talking about next. It also drove the motors too. For that, we need an Arduino Nano. This would send out PWM signals, which were in charge of driving the motors. Those signals also went to our Kryton motor controller, and that is what powered the motors.
Hello, I'm Wyatt Jordan. I'm our team lead and software lead for this project. And we started looking at what sensors we needed in order to complete the tasks that the competition entailed. We needed to pull in data about the environment that would tell the robot enough to navigate safely and find the candle and extinguish it. So one of the big problems with this competition is localization, which is determining where you are in the maze, where the robot is as it's running. And for that, we were going to use this LiDAR sensor, which uses a laser that's being shot out as it rotates 360 degrees. And this is the same technology that many autonomous cars are using and being used to develop autonomous cars. We were also planning on using camera and some infrared sensors, and these are basically secondary measures to make sure that what the LiDAR is seeing is actually true. So if we spot a candle and drive up to it, we want to make sure there's actually a flame there. And if we drive up to the crib that the baby was in, there's some computer vision targets on the side of it, and that would allow us to confirm that's the target we're looking for.
Okay, so my name is John Walton, and my main contributions to the project were mechanical design and finite element analysis. You can see here our conceptual design, some of the criteria that we need to look at for the initial design of the robot. We had to come up with an overall structure, and so we chose a 3-tier circular design because the 3 tiers gave us a lot of versatility in the way we could arrange components on the robot. And the circular design, because the footprint of the robot was smooth, and if we went around corners and caught on things, it would be less likely to throw off the robot. We also chose a differential drive, so that means we've got 2 motors that can rotate in opposite directions for turning, and that makes the robot be able to turn on a dime. that's located on the center of the robot so that the footprint of the robot does not increase during the turn. We also had to employ 2 caster wheels, one in the front and one in the rear of the robot, and a shock system in order to keep the robot balanced as it moved around the maze and went up a ramp. And Bryce will talk about that later.
So the medium that we chose to utilize in order to print these parts, we decided to go 3D printing because it actually just gave us a lot of freedom to be creative however we wanted. We didn't want to just have to use a slab of material and chop that material to whatever dimensions we wanted it to fit, but rather we wanted to be able to incorporate components to actually make it more structurally rigid and stable. So we decided to use 3D printing. The material that we chose to use was onyx. Grove City College has a great Markforged printer that's able to use this carbon reinforced nylon called onyx. And this onyx material is a lot more structurally rigid and a lot more durable than any regular nylon material that would have been printed. One of the problems that we encountered when we were utilizing this printing was that the print envelope was too small to print the entire base of a robot. So last minute we had to make some adjustments in order to make that base part that we had divided into 3 components. As you can see here, the parts are overlaid with each other and then secured together with either adhesives or hardware. One of the most important things early on in the project was to get a ground level base to the electrical engineers so that they could get started as fast as possible with everything they needed to do. Because the early part of the project was mechanical marginally, we wanted to get that as quickly done as possible just so that they could start working on motor controllers and things of that nature. I was the engineer in charge of the base level, and so here you can see the first model. We modeled everything in 2 iterations, so we got to learn from our mistakes and make a lot of changes. The first model worked really well. It had motor supports down the middle, along with hole cutouts for the 2 wheels that were going to be held on the motors. As we said, it was a 3-tier design, and it had standoffs going up to the second level. And we also utilized the use of ribs vertically just to add a little bit more rigidity because we weren't aware that we were going to have to break it up into 3 pieces at first. And so we added ribs in order to make that a little bit more stable. Some of the issues with it, however, were that it was still a little bit bendable, and that had a lot of factor in the error when we were actually driving it, and the wheels couldn't stay as stable as we wanted them to. It also didn't have any storage for batteries. We have 2 batteries that we wanted to be on this first level, and they were kind of just falling out of the robot, and it didn't have storage for other things like water tanks or water pumps. And so we really utilized these things that we needed to make changes to when we made the second iteration. The second iteration looks like this. So as you can see, there are now motor supports, but there are also C-brackets that not only connect to the motors, but they connect to the levels above. And this allowed for not only structural rigidity within the first level, but between the 2 levels, keeping them completely secured together. We also have components such as an area for a pump, area for water tank, and that blue up into the top left is one of the batteries in a component that goes up to the top, adding that extra bit of structural rigidity. I was also able to work on a caster wheel shock system, essentially just springs on rods that keeps these caster wheels compressed to the point where the LiDAR would be completely balanced and not scanning too low or too high, missing anything that might be vital. And that is right there. Now I'm going to pass it off to John Walton to talk about level 2.
So this is the design for the second level, and it benefited a little bit from some of our knowledge that we gained from Bryce's level 1 design after that of printing. And so additional ribs were added to this design. You can see the ribs span both vertically and horizontally, as well as ribs that go around each of the mounting holes for the different circuit boards. A couple things to note on this design would be another attachment. The attachment between the 2 pieces on this design was improved from the first level design. If you go to the next slide, then we've got this compared to the current design. This is the second level design that's currently on the robot. And a few improvements that we made from this design to this design, based also on our finite element analysis that we did prior to this. You can see there's additional ribs for added rigidity. The attachment method is actually changed so that there's no stress line that runs directly down the center of that part. It's broken up so that it spreads that out a little bit more. You can see these wire slots around the threaded rod have been increased in size on this second design so that we can fit tubes that were a little bit larger diameter up through there. Additional wire holes were also added to the middle of the design, and more mounting holes were added. A significant part of this second level design was getting all of the holes located for the electrical components. As we gathered information, we were able to figure out where the holes needed to be in order for everything to line up well electrically. And that's the biggest improvement, practically speaking, from this first second level design to the second design.
Well, hello everyone, my name is Jonathan Lees, and I was a mechanical designer for this team, but I also had a couple other minor roles, such as the primary writer for the team. I would keep minutes in our meetings, and I edited our technical report. But I'm going to talk to you a little bit about my main contribution to this project, which was to design the third level of the robot, as well as the arm system, which is used in level 3 of the competition. So, as Bryce had talked a little bit about in the beginning of the presentation, the contest that we were entering had 3 different levels. And level 3 was very similar to levels 1 and 2, except it had an added objective of locating a baby in a cradle somewhere in the maze, picking it up, and carrying it to a safe zone. So if you look at the slide, you'll see a picture of the baby. It's very, very small, only a few centimeters. And you'll see a drawing or a depiction of the cradle, which is only about 12 by 12 centimeters and about 10 centimeters high. So there were several design considerations that we had to take into account when we were thinking about how we were going to tackle this objective. The main ones were that we couldn't obstruct the vision system when we picked up the cradle. And as Wyatt kind of talked about, we use a LiDAR system, which is the same technology that's used in self-driving cars. And how that works essentially is it's a rotating signal, and what that signal tells us, or tells the robot, is how close it is to objects surrounding it. So when we picked up the cradle, we had to make sure that we didn't obstruct that. The other thing to consider is once we have the cradle in the robot's grasp, it still has to navigate the maze. So we want to lift the cradle in such a way that it doesn't change the geometry of our robot, which would complicate navigation a lot. And then there's some rule constraints. As Bryce said, we have to fit a robot in a box prior to starting the competition. It also says baby orientation in the cradle. What that's referring to is this year's rules specified that the baby will be placed in the cradle like so, which did affect how we designed to tackle this objective. So the first idea we had was a simple forklift design, but we ruled that out pretty quickly, mainly because it would obstruct the LiDAR, and it would definitely complicate the geometry a lot because we would be carrying the cradle in front of the robot. So we decided that we wanted to implement an arm design, and how that would work is the arms would be folded on top of the robot so that it would fit into the box. They would extend when we actually needed to lift the cradle. So the question really became, how are we going to securely grip the cradle? So the first idea we had was a slide design, and basically that would have an additional motor on the end of each arm that would slide some sort of gripper into the slots that you see in the cradle. But once we got this year's iteration of the rules, obviously that wouldn't work because the feet are actually sticking through that slot. So we have the design that we decided to employ here with an arm and hand design. And how that works is essentially we use a combination of servo motors to give us multi-axis rotation. So you can see here we have a depiction of a 3D axis, and how this works is once the robot identifies the cradle, it will approach it, and then the arms will swing around about the Z-axis and grab the sides of the actual cradle and then lift it up over the top of the robot, rotating about the Y-axis. This really worked well with our design considerations because not only would it not impede the LiDAR's vision, but it also would ensure that we retained the same geometry for navigating the maze after we've lifted up the cradle. And now Wyatt's going to talk a little bit about the final design of the robot.
Right, so this is our second level here, and as you can see, the LiDAR sensor is mounted directly in the center of the robot, and that allows us to not have to transform the points between 2 different reference frames. So the robot has its own reference frame, and then there's a global frame, which we'll get to in a minute. But by putting the LiDAR right in the center on the pivot point of the wheels, that completely eliminates the need for a third transformation. As you can see here, all the major electrical components are mounted and this is the completed design of the third level. So as I was saying, we needed to use localization to convert between our global frame and the robot's frame, so that the robot can actually determine where it is in the maze. So one of the main methods we have for doing this is using the encoder counts on the wheel. So we can calculate the rotations of each wheel, and based off of that, we can, if we average those rotations, we can find the robot's travel in its own x-coordinate frame, and then we can also, by the difference of those rotations, determine the robot's rotation in its own frame. Once we have those two pieces of information, we can form a step in the robot frame where we were previously and where we are currently, and we can then transform that step using a rotation matrix around the z-axis, because the robot itself is going to be translated and rotated somewhere relative to the map. And then once we've transformed that step, we can then rotate it into the global frame, and then we can add that step to our previous global location. So we have a global location previous, a global step, sum the two, and we get our next step. And this is happening at about 50 hertz.
So my name is Eli Dad, and my main focus on this project was the LiDAR system. And so the LiDAR, it takes distance measurements from the walls inside of the arena to the robot. And this does a 360-degree scan, so it knows its environment. And so what we do with this data is we create line models. And so we're doing that by taking 2 points, and then we'll take a third point and check it with that line model. If it fits that line model, it will then add it to the line model and then update the model. It will keep doing this until a point doesn't fit that line model, and then it'll just restart. And it'll do this for the whole 360-degree scan. And so with this data, we will be able to determine which room we're in. We'll be able to determine the location of the robot. And so we can find the candles and the obstacles in the maze based off of these lines and the jumps in between the points.
Right, so as Eli was saying, we're using our LiDAR algorithms to gather not just random points around us, but actually form models which are more useful for localization. One thing that is crucial when you're developing a map model, which is what the robot's using to know where it is in the maze, is to know what features of the maze you can actually sense. So you need to know exactly what kind of data you're pulling in, what kind of anomalies that data has, outliers, and other random things that are going to try and throw it off. So that was a very important lesson we learned when we started testing this, and we already had some ideas of how to develop our map. What we wanted to do was use these lines and find the endpoints of the line segments. And we wrote an algorithm that, given a robot location in the maze, it can determine all the endpoints that should be visible. So as you can see here, all these endpoints are in green that the robot has a direct line of sight to. This isn't as good of a method as we originally thought, because as you can see with this wall, it's very tangent to the robot, and so there will be very few points because the polar width of that is very small. So another big advantage is not using single data points like that. If you use single data points, you're very susceptible to outliers or noise heavily influencing them. But rather, if you use a line model, you're using all the points in that line, and it's an average, so it's not going to be as susceptible to outliers. And another major thing we learned as we kept working on this was to keep it simple. If you make code that's more universal and more elegant, but you can't debug it, it might as well be useless. So this is just a demonstration of the robot detecting furniture, which it does by finding a jump on either side of each piece of furniture, and then determining if there's a slight curve in front of it, and so it can track these objects in the maze. And the yellow lines are being formed from the LiDAR data as well. So the main network we're using for our software is the robot operating system, which is standard in industry, and it's a node-based network for integrating sensors, which are running in parallel in the entire system. This is the industry standard. Many research groups are using this software, and there's a large amount of support for it. Our network is fairly small, which is nice. Here we have just a node that's pulling in our sensor data and doing all the math to calculate the points around it. And that's coming from a software package provided by the manufacturer of the LiDAR. There's a core node which handles communication between other nodes. And we built our own package called the Firefighting package, and that has 3 main objects or C++ classes in that node. The first is the robot class, which handles all sensors besides the LiDAR and the drive motors and other things dealing just with the robot. The second is the navigation class, which handles the map model, waypoints for driving in between and through the maze. And the third is the LiDAR class, which handles processing the LiDAR data and forming those lines we were talking about. So as these three different classes are running, they're running separate threads in parallel. So the robot class has one main logic thread where it just says, go to this room, check if there's a candle. If there's a candle, go spray it out. If you found a candle, stop. Otherwise, keep going through the rooms. So it's very high level, but there's a lot of stuff going on in the background. And the main thing is this drive loop, which is operating at 50 hertz. This is calculating the odometry position based off the encoders. And then it's checking if the robot is ramping up its speed to slowly increment the speed as this is running. And it's also running a PID control loop, so proportional integral derivative control, which is then allowing the pose of the robot to be set, and based off of where it currently is and the amount of error, it will adjust to be where we want it to be. And then all of that adjustment, it's then going to change the motor values. And this is running in real time, 20 milliseconds every loop, so 50 times a second. As this is running, the LiDAR is also running in parallel, and that operates at 10 hertz. So every 100 milliseconds, we're getting a new scan of data. That new scan is then processed, and this thread gets information from the robot class to determine if a linear movement occurred. And the reason for this is we don't want to do our processing when we're rotating, because the sensor is rotating, and if the robot also rotates around the coincident axis, then all the data becomes very messed up. So if we determine there's a linear movement, then we'll process the data, find the jumps, find the furniture, and then we'll send the line models and the current position over to the navigation class. The navigation class knows the map model and now has the lines around the robot and the position of the robot on the map. So from this information, it can determine which direction the robot is facing, and it uses the nearest wall by its side. That should be a parallel wall to the robot. And once it finds that wall in the global frame and what its actual value is, it compares it to the value that was read by the LiDAR, and then it sends an update back into the 50 hertz loop here. And this gets seamlessly integrated so that there's no hard stops, there's no data dependencies, it just keeps running. So for those of you who didn't get to see a live demo, we have it on video. This is starting from unknown start location. And over here, the visualization will appear in a minute. And you'll see red dots, which are the LiDAR scan data, and the yellow models, which are the lines that are being formed from that LiDAR data. Here you can see this wall has green markers right now. That's because that wall was just used for a location update. And these markers here are set in green when the robot traverses the blue graph, which is the waypoint graph. So we also made a path planning algorithm which will find the shortest distance between any 2 points in that path planning graph. And so here it's searching for the candle, and it doesn't find it, and so now it's highlighted all of these points, which it's going to traverse to get to this ring. Any error that you see, such as this line not matching the global line, is the error between where the robot thinks it is and where it actually is in the world frame. So you can see during rotations that error spikes up pretty good. That's because the robot is turning and needs to figure out after the turn how much it's turned and how much error is accumulated. And then here it's found the candle, it's created a new waypoint to drive to, and extinguished it.
So before Eli wraps this up, it is important to mention a few things about our budget. We did have a financial constraint of $1,500. Of that, we spent about $1,100. Most of this was spent towards a lot of our major components, including the Odroid, the LiDAR, and the motors. This is a picture of our budget sheet, and this was very useful. We were all able to access this and put information onto it. That allowed us to easily see what parts have been ordered, what date they may need to arrive, parts that need to be ordered, and parts that we're going to cancel. This is a graph of our sensitivity analysis. This shows the percent cost versus our different expense categories. As you can see from this bar graph, the computer was a significant portion of our budget, with almost 40%. If that were to change, that would have a very significant influence on the total project cost. This graph, a Pareto plot, this shows the percent of each one that's added up together, as well as the total cost of each expense category. And what you can mainly see from this is with our major components, like I said, the motors, the LiDAR, and the computer, we were up to almost 70% of our total project cost.
So as Bryce mentioned earlier, we were going to go to Trinity College's firefighting robot contest. Sadly, due to time constraints, we would not have been competitive at the time to participate in the contest. So we decided to focus more on our mechanical and software issues at the time. So right now, we do have a functioning autonomous firefighting robot that can determine starting location, and it can determine what room it is in. And so it can extinguish the fire, as the video showed earlier. Now I'd like to thank Dr. Bright, our advisor, and then Mr. Gillette. They both helped us tremendously throughout this whole process. We would not have a robot without them, so we gladly appreciate what you've done for us. Now we'd like to open it up for any questions that you have for us.
The LiDAR spinning thing on top there, how does that work if there's like fog or smoke? Like for self-driving cars?
Yeah, that's a good question.
Or,
It doesn't.
Smoke in the building?
Self-driving cars use three main sensors, which are LiDAR, cameras, and there's a third that I'm forgetting. But they need all three to be able to navigate in all forms, all environment, all weather conditions. Yeah. But LiDAR is a fantastic sensor for that application. On any clear day, those LiDARs can see 200 yards out. Yeah, they're very good. Yeah, John.
How did you keep the LiDAR from seeing the posts? I noticed there's like in that picture, there's like 4 posts on the end. How did you like come that out or keep it from reading?
So the LiDAR does see the posts, but in our code, we are able to filter out specific distances of the LiDAR. So basically we said anything within 18 centimeters, just ignore it. And so that wouldn't mess with any of our line models.
Are you using LiDAR to detect the candle as well?
Yes, yeah, so the candle is 2 centimeters width. So it's looking for that 2 centimeters gap in all of the lines. And then we also have an IR sensor that is also capable of sensing any heat. So that determines if the candle's lit or not.
I was curious about, because I think you mentioned that you couldn't, your LiDAR data wasn't good when your robot was actually rotating. And I'm wondering why that is, because it seems like you would know your angle of your robot, so couldn't you compensate for that? What was the problem there?
So I think it can't keep up with how fast that angle is changing. That would be my guess. There's also another loop that's running, which is publishing just a transform between the global frame and the robot frame. And that's what's actually being used to visualize the data. And that might be only running at 10 hertz, which would, the other one's running at 50. So it would be a little bit laggy. That might be part of the reason. So it could just be some of the visualization, but just the fact that as you're rotating, the axis, it's the exact same axis that the sensor is on, having to do that at the exact same time.
How fast does the LiDAR spin?
10 hertz, so 10 times a second.
10 hertz, so the robot would be a significant fraction of that.
Yeah.
So the end of your cycle would be different than the beginning of the cycle.
Right, but you would know, you're updating your robot angle all the time, so it seems like you could, there's probably a way to.
Yeah, I'm sure if you really wanted to make it always work at that time, you could, but for our purposes, it wasn't necessary, so we just checked if we're spinning. Just don't worry about it. We can update later.
Okay.
Do you see like building owners buying these and keeping them in a building to like augment a sprinkler system or something like that?
The best application I could think of would be warehouse fires. If you have a very large warehouse that's a fairly open environment, That's something to get to very quickly without having to send off an entire sprinkler system and ruin all inventory. Yeah, something like that would be your best application.
And one application of it, in Notre Dame, they used a firefighting robot to help fight the cathedral fire. The main difference between this and their robot is, well, first off, theirs is much more advanced than ours, but theirs was human controlled, so ours would be autonomous.
The Navy also has an autonomous firefighting robot on board some ships, which was within the past decade.
I have one more question about the arm mechanism. Were you able to test that on the cradle, and how well does it lift the cradle up above the robot?
So the arms are built, but they're not yet functional, mostly due to time constraints. As Eli said, when the time of the competition rolled around, we weren't able to be competitive. I think if we were to enter now, we'd be competitive up to level 2, but not level 3.
I'm not sure if I'm right or not, but in the video when I put out the candle, I thought there was a sweeping motion. Was that a loop or something that you created that would, once it sets the candle, it would have a little bit of motion back and forth?
Yeah, and that's triggered by the IR sensors, and then it's turned off by as soon as the IR sensors detect that there's no more heat source there.
Does your robot know where it's been or just where it hasn't been?
You could save that data throughout the whole course if you wanted to. Yeah, you could just push it onto a stack and have a whole stack of where you've been.
All right, thank you, folks.
Thank you guys very much.